Yeah, okay, thank you. So let me pull out my PPT. Just confirm if it is visible because sometimes it's very difficult. Is it visible, my PPT?
Not yet, sir. No, sir, it's visible. It's visible.
Okay, okay. So, okay. So today's topic is linear disk analysis, supervised technique. Okay. So there are two approach for dimensionality reduction. So one I think you have done in I think in one of the class. So that was your principal component analysis, and also I think a professor has touched this LDA as well. But today I'll try to explain a bit, uh, in a way that you can understand it with an example. Okay, so linear discriminant analysis is a supervised dimension reduction approach. So second screen is visible or not? 1 minute. Just give me a second. 1 minute. Okay. So I'm on second screen. I think it was not moving. Okay, now. So coming to this, I will be touching this dimensionality reduction, LDA, and where you can use this linear discriminant analysis and when to use this linear discriminant analysis. And also this linear discriminant analysis is similar to your, you can say, logistic regression. It's a similar. Somehow you may get confused with some of the classification algorithm. So LDA has some of the, you can say the features of this logistic regression. So we'll try to distinguish it, how it is similar or different from linear discriminant analysis. Okay. So coming to this linear discriminant analysis, and also I have some applications to show, and I'll use R and Python as well, how you can apply this linear discriminant analysis. Okay. So you might have heard of there is something called positive discrimination. Okay. So discrimination itself, if you see this discrimination itself is a bad, it's a bad word. So what is positive discrimination? If anyone can tell or anyone can type it, what is positive discrimination? I think everyone knows what is discrimination. Sometimes we may face, discrimination based on gender, caste, creed, maybe religious discrimination. So we all face some kind of, yes, some kind of a privileges. Okay, so positive discrimination is, yeah, it's some kind of a privileges that we usually, get it. So that is positive discrimination. Okay, so sometimes it is good, but not every time. It's not like that, you provide these privileges to sometime. For example, if somebody is disabled, right, you offer seat in a metro, maybe the elderly people, right? So you can classify them as a positive discrimination because you are discriminating yourself and offering seat to that elderly people, right? So it's a kind of a discrimination, but it's a good, right? So yeah, and also you will face this kind of a discrimination also in your, office and all, right? So why discrimination is good? So sometime, discrimination, as I already said, it's a bad when the discrimination achieved is used in a negative way, right? If you're trying to differentiate it in a negative way, then it is a bad, right? So otherwise you can do a lot of good thing using this positive discrimination. So I'll tell you how you can apply this kind of a positive discrimination in linear discriminant analysis to come up with two class labels or for multi-class labels for classification purpose, right? So discriminant analysis is a loose derivation, you can say, from the word discrimination. Is a concept widely used to classify labels of an outcome, right? For example, if you're trying to flip a coin, either you're gonna get head or tail, right? If you are providing a loan to a particular person, right, he may get, you can say, he may get sometime defaulted or not defaulted, right? There are two classes. If you are running a company, employee may churn or not churn. So that is a classifying the levels of an outcome, right? It is useful in determining whether a set of variables are effective in predicting category or that membership, right? So if you want to provide loan to particular person, so how you are going to come up with certain factors which are effective in predicting the category or membership, right? So this is how, using the discriminatory approach, you can say the positive discriminatory approach, how you are going to classify, right? So that is why sometimes you can say the discrimination is good, right? So now, so you might have seen this visual somewhere. So dimensionality reductions are of two types. If you have a features, you can say, where you don't have a output combinations of those input features, right? So that will come under unsupervised learning approach. For example, if you only are left with the input features, or you can say that you only have the features with you, you don't have any target variable, dependent variable, for that matter levels. So in that case, you will apply this dimensionality reduction approach that has some element in supervised learning and unsupervised learning. Okay. For example, if you want to give loan to particular person, obviously you will have, let's say, 10 to 12 features. Based on that features, you are predicting whether you want to give loan to particular person or not. So that will come under supervised learning approach, because you are using 12 or 13, maybe 15 features. So it's like a huge features. You can't use every single features for predicting whether you want to give loan to a particular person or not. So that is why you will use this LDA. You will try to reduce the dimensions. If you are using 15 features, you will try to reduce it to maybe 12, 13 or something. And then you will try to predict the class level, right? So that is your LDA. So LDA, what LDA does is they try to reduce the number of features, and also they try to do the classification job, the way I taught you this logistic regression, right? So that is why it's similar in that sense, but not, you can say, the same thing. They are not doing the same thing, but doing the similar thing, right? For example, a model with too many degree of freedom, it means they have so many features. So if you have many features, it means they are going to overfit the model. If you are bringing any test data, unseen data, they are going to predict it, because they are trying to memorize the entire row, you can say, in that model. So in overfitting, obviously this will give you a better result in the test data, but it's not a good, you can say, it's not a good way, right? So training, I mean, overfitting means your training data will have a more accuracy, but test data will have a lesser accuracy, right? So there are a large number of techniques to reduce these dimensions. Apart from this LD and PCA, you have a many techniques, forward, backward, feature selections. There are many, right? But this one is quite interesting, because you are also at the same time, you are reducing the dimensions, you are reducing the number of features, as well as you are doing the classification job, right? So no other algorithm does this. So linear discriminant is a powerful. They uses typically the linear transformation, or you can say a combination of linear, you can say, features, and they try to predict the class, or you can say the output or target. They use the linear combinations of features. That is why we typically say linear discriminant analysis, because they use discriminant function or discriminatory approach, right? So LDA is a supervised dimensionality reduction technique, and the goal is to project a data set onto lower dimensional space. So this word lower dimensional space means you are trying to reduce the number of features, right? So lower means they will create one more, you can say the dimensions also you have with a good class separability in order to avoid overfitting, right? Overfitting means, I mean, whenever you come up with a new or unseen data, they are giving you some, output. So, I mean, overfitting means your training data set has a more, you can say the accuracy. Maybe if your training data set is giving you, let's say, 99 or 95% accuracy, but in test data, whenever you are bringing a test data, they are not giving you that much accurate result. Okay. So there is something called curves of dimensionality. Okay. So if you are using more, you can say the features in building any ML models. So in that case, there will be a case of overfitting, right? So just to reduce the, you can say the computational cost, because for every single features, you require some kind of a bit to compute it. That is why it's better to use less number of features in case of predicting any class labels. If you are using any classification algorithm, it's better to use less features so that you can reduce the computational power, the computational cost. Okay, just see this one, the right figure. Okay, so here if you see this one, the right figure, this one, let's say for example, this red dot, let's say this is a churning of a customer, let's say, and the plus sign is not churning of a customer based on some feature, let's say X and Y. Let's say based on age and salary, for example, I'm just taking two features here. It could be many because it's very difficult to project it in a multi-dimensional way, but I'm just using two features. Let's say age and salary. Based on this age in x-axis and salary on y-axis. Okay, so we are trying to predict the class, right? Here already we have, based on the test data, now we have two, you can say the class. One is churn plus one is not churn, let's say. Okay, now had it been, let's say, 10-15 features, and based on those 10-15 features, if it looks like this, then how we would have reduced the number of features, right? So now if you see the logic here, the logic of this LDA lies here, right? Let's say I have projected one more, you can say the axis here, let's say. If you draw you can say the variability of this data, the mean, standard deviation and all, then it will look like this, right? So if you draw there you can say the variations. So this bell-shaped curve is capturing the variation of this class. Let's say not churn. And this bell-shaped, this red one, this bell-shaped is capturing the variation of this class. This is a churn class. If you see, there is a separation of this class. There is a well separation of this class. There is no such, you can say, the class which are in between these two, right? So this is a good way of projecting this, you can say the LDA axis. So this one is a good way, LDA one. This will give us some, you can say, the coefficients based on the features. Let's say this was age, X, and Y was salary. Maybe there are another features, you can say X, Y, Z, A, B, C, D. These are the some dimension, let's say, based on the features. If you see this one, LDA2, these are the another component, you can say. If I project like this, if I project like this, if I project like this, so in this case, just see, these two are overlapping. Just see, right? So these two whale-shaped curve are being overlapped, right? So this is not a good, you can say, LDA projections, right? But this one is good. So ultimately, in this linear discriminant analysis, we will try to achieve maximum separation between the two class, and there should be maximum variance within this class, right? This is the typical, you can say, the crux of this linear discriminant analysis. Okay. Okay. So if you have any question, you can ask in between, you can type in. Okay. So, okay. So just see this visual. There are two features. One is GRI, another one is AGR. These are two features, and these are the two class, right? These are two class. Let's say this one is, red one is, let's say, now just take one example of your, these are the defaulters. Red one is defaulters and blue one is non-defaulters. Okay. So in this LDA, what LDA will does, when you will apply LDA in R or Python, they will try to maximize the class separation, right? If you see the between the class variance, they will try to maximize the class variance, but within the class variance, they will try to see if it is, maximum or not. Within the class variation should be, minimum, but between the class should be maximum. Okay. So using the discriminatory approach, they will look for those axes where they will achieve this between the class variation maximum, but within the class variation should be minimum, right? So this is the approach of linear discriminant analysis by using this discriminatory approach. Okay. This is what these visuals are saying, right? So linear discriminant analysis, a linear machine learning algorithm used sometime for, also you can use it for multi-class classification, right? And LDA is also used for compressing the supervised data. Just see this word, compressing supervised data, right? Compressing means whatever features you have, they are trying to compress it. They will compress it. I'll show you how. Okay. So when you have a large set of features and our data is normally distributed, this is very much important. If your data is normally distributed, okay. For example, if you are doing any sampling job, for example, if you have captured data through some survey, so normally the data which you have captured through survey on, let's say, nominal scale or maybe on a Likert scale, the tendency, or you can say the feature of that data is they are normally distributed. Typically, if you are able to plot it. If somebody is capturing, let's say, consumer satisfaction based on 1 to 5, let's say on a Likert scale, that is called Likert scale. So if you capture 100 such, you can say the data points, if you plot it out, you will see the data are normally distributed. Any data which are drawn from survey are normally distributed. So the feature of this normally distributed is that they show whale-shaped curve. Okay, like this. So, okay. And our data is normally distributed and features are not correlated with each other, then you can use LDA. So if you are trying to use LDA, just try to see if the data is normally distributed or not, and also just look for the features which are not correlated. Had it been, you can say, the highly correlated data, LDA will give you not that much good result. Obviously, there will be some overlapping of the two class if it is a two class problem, right? So linear discriminant analysis, it typically seeks to best separate, right, as I was using this word, or discriminate the samples in the training data set by their class value, right? Especially the model seeks to find the linear combination of input variable that achieve the maximum separation for the sample between the class and minimum separation of the sample within the class. As I was saying, minimum separation should be within the class, but there should be maximum separation between these two classes. One is, let's say, defaulters, one is non-defaulter, let's say. Okay. So LDA, as I said already, if there, let's say this is a defaulter, blue one is a defaulter class, okay, and this red one is a non-defaulter class, let's say. And let's say I have projected one line like this. I have projected one line like this, and I'm just trying to capture the variance. If I will capture the variance, these are the bar chart, right? Bar plot, you can say the histogram, right? So if you plot it out, you will see something like this, a bell-shaped curve, right? But you see there is some overlapping here. There is overlapping in the projected space. So what LDA does is they create a new, you can say, axis where there should be less, you can say, the maximum separation between the class. But here there is a blue and red, there is a overlapping. It's not a good projection, right? But if you see on the right side, if I project a new axis like this, okay, if I project a new axis like this, then just see, there is a clear separation between these two classes, right? So this is a good projection. So if you apply LDA in this type of classification problem, then they will give you this projection. This one is, let's say, LDA1, this one is LDA2. So LDA2, this projection or this axis, new axis they create is providing this axis is providing a better separation between these two classes. One is, let's say, defaulters, another one is non-defaulters, and there is a clear separation between these two classes. Okay, so this is a typically job of this LDA. Okay, so LDA projects the data to a lower dimensional space. Lower means it was, let's say, 5-6 dimensional data. Now they are projected in a single dimension. So they have reduced the dimensions, right? So the point belong to different classes are more spread out now. Just see the class, this one, the belong to this class and this class. Now they are highly separate, you can say spread and highly separable, right? Between the class covariance as compared to the spread within the class. If you see, there is a the data points are compact here within the class, here also, but these two between the class there is a clear distinctions, right? So this is what LDA does, right? And the better LDA projection is this one, the right figure. This is not a good way. If you project like this, just see, just imagine it. If I project a line like this and I draw this histogram, there will be just these points will be highly, you can say, overlapping. If I plot like this line and I draw histogram, these points and these red points, these blue points and these red points, there will be highly overlapping. So this will be not a good, you can say, LDA projection. Either you can do like this or like this. So LDA, what LDA does is in every single iteration, they try to come up with a new axis where they try to minimize, you can say, the maximize the class separation. And once they get that axis, they give you the result, right? In R or Python, in any software, right? So this is a clear, you can say, the concept behind this linear discriminant analysis. Okay, now it is moving. Okay, so this what I was telling you. This is a good projection. Okay, so coming to this example. So if you see this example first, so consider there is a simple problem, and in which we try to decide whether a drug should be given to a patient or not, right? So our features, let's say there are two features. One is gene X and gene Y. Okay, gene X and gene Y. And we will have two labels. So obviously the blue and red, let's say this is red. There are two class labels. Based on these gene X and gene Y, gene Y and gene X, we are trying to create a visual where we have a two class label. One class label is where you can say the drug worked, and other class level where drug didn't work. Okay. So there are two class labels based on these X and Y features. Okay. So how LDA, how we are going to create a axis, just think of axis. Should I create a axis like this? If I create, let's say, if I create an axis like this, and if I project all the, you can say the class, there will be overlapping of these. Just imagine it. These points will be overlap with this blue. These class will overlap with this blue class. So this is not a good way. First, now, if I project one axis like in a y direction, just imagine like this, and I project the variation, you can say. So there will be overlapping. These all data points will overlap, or let's say this blue will overlap with these data points. This one, you can say this one will overlap with this. So there will be much overlapping even in this kind of LDA projection. If I, let's say, project a line like this, if I project line like this, I think I will be able to capture the variance in a better way. See, if I draw a line like this and I capture the variance, then in that case, there will be some kind of, you can say, separation. So let me show you how. So yeah, if I project LDA like this, just see how I'm getting. So there is some overlapping here, and there is a no clear class separation. If I draw like line like this, the two classes are not being separated. If I draw a line like this, even there is a two classes here, but there is no clear, you can say, the distinctions. If I draw a line like this, there is a class separation, but here also we are misclassifying these three class labels, one this and two this. So also this is not a good way, right? So it's a bad way, you can say the bad approach of this problem would be to project the data point in x-axis, right? So this would, what typically this would imply, losing a lot of information from the y-axis, right? So what LDA does is that it projects the data onto new axis in a way to maximize the separation between the two. If still we are not able to create a maximum separation between these two, red and blue. If I draw like this, even we are not able to create a maximum separation. So there is a problem. So now how we are going to project a new axis, or how we are going to create a new axis? If I draw a line like this, okay? If I draw a line like this and I capture, it's like a, you can say the magnet, this line, a point will be, stick to this line. Okay. This will like, this, you can say the class will stick to this point, this one, something like that. Okay. So if I project a new axis like this, if I draw like this, just see, there is a class separation, but there is a misclassification of this class. But still we are able to create a new dimensions by, at least you can say, clear separation between these two class labels. Okay. So this one could be the best, you can say, the LDA projection, at least. So in LDA, whenever you run in R or Python, they keep searching for this, you can say, the axis where you can create a maximum separation between these two class, and you can say the minimum separation within the class level. There should be minimum separation within the class, but maximum separation between the class. So this is a good projection, you can say. If I draw a line like this axis, I have created one, and I projected all the data points here. So now there is a clear, you can say, separation. So this is a good, you can say, the projection, right? Now see, if I collected all the data points like this, there is a, separation, you can say this is a misclassification. Or if I draw a line like this, so there is a one misclassification here. and all are good. So this could be the best way to project a new axis. Okay. So new projection on x-axis is a good LDA, right? So this is a good projection. So we will look for this. Okay. So maximizing the distance between the two means, okay. So how this new axis created, you have seen it, okay, obviously through some, obviously hit and trial methods, but there is some maths behind that. LDA typically look for those regions where there is a maximum separation between the class. They look for those, you can say the axis, right? So new axis should be maximize the distance between the two means. So plus you can just think of this mu plus and mu minus. Okay. So mu plus and mu minus is the two means, you can say, of the class. Let's say blue is defaulters and red is non-defaulters. Okay. So there should be maximum okay, distance between the two means. So mu plus and mu minus, it should have a maximum distance. But mu plus within this class should be minimum. But mu plus and this red mu minus, their separation, you can say, should be maximum. Then only you will able to create a clear distinctions between these two, let's say, defaulters and non-defaulters class. Okay. So the new axis should be minimize the variations scattered within the each category. Okay. So the sigma plus and sigma minus, it should be maximum, right? So if I draw their variance, you can say sigma plus and this is sigma minus. There is overlapping, but not that much. There is only one, you can say, the class which is overlapping. So at least this is a good projection here through the data points, whatever given to us, through the observation, whatever given to us, at least. So the job of this linear discriminant, as I already said, is to have a maximum, you can say, variations, maximum distance between these two, you can say, the class. The variance should be maximum between the class. Okay. So how you are going to optimize it, right? So how typically you are going to optimize it, that is the challenge for us. Because ultimately, if we will not optimize the case, we will not achieve the clear distinction, or you can say the clear separation between these two classes. Okay. So just see in the previous, you can say this visual, this was mu plus and mu minus. Okay. Mu plus and mu minus, and sigma plus and sigma minus. Okay. Just see. So mu plus and mu minus, there should be maximum variance. You can say the minimum, you can say the mean should be there within the class, but there should be maximum, you can say the variance. Okay. So numerator should be ideally be large, and this is the denominator should be a small. If we have a 3 class, then how we are going to do that? 1 minute. If you have a 3 class, then you can increase sigma plus, sigma minus, and mu plus and mu minus, and then only you can achieve this. So this is a distance typically. Okay. So now just see this one graphically, as I think I have already explained to you how graphically you can represent this linear discriminant analysis. Let's say if you have a two variable, variable 1 and variable 2, let's say you are predicting, let's say, defaulters and non-defaulters only based on, let's say, variable 1 is age and variable 2 is, let's say, salary. Okay. And based on this, let's say this black one is defaulters and this, let's say, green one is a non-defaulters. How we are going to classify it? By reducing the dimensions. Here it is only 2 features, but as I already said, just imagine it, let's say 15 features, and based on those 15 features, I have created these visuals, and the visuals look like this of 2 classes. One is defaulters and another one is non-defaulters. If I project a line like this and I capture the variance here, just imagine it, the variance will look like this. So still there is some overlapping here. Okay. if I project line like this, just see, there is less, you can say, there is a more separation. Okay. Here there was a less separation between the class. Okay. But here it is a maximum separation between the class. So this one is a good LDA projection, a new axis. This is a good way. Okay. So we will discard this one, but we will retain this one, this LDA projection. LDA is nothing but creating a new axis and then capturing the variance. Okay. So here you can see there is a clear separation between these two classes, defaulters and non-defaulters. Now just see this one. This is another example. I think you have seen it. This is, let's say this is age and salary. If I draw a line like this, then there will be more, you can say, overlapping. If I draw a line like this, there will be more, you can say, the overlapping. If I draw a line like this, there will be less, you can say, the overlapping of these two classes. Just see, there is overlapping, but there is a less overlapping here. So in confusion matrix, if you look for this confusion matrix of any classification problem, so in which you will reduce, able to get less type 1 and type 2 error. But if I just retain this one, I will have a more type 1 and type 2 error, you can say, and here you will have almost 0 type 1 and type 2 error, because they are clearly classifying the class. Okay. So this is how graphically we represent this LDA. Okay. I think, hope you are able to understand at least the concept how LDA works by separating these two class level using this discriminatory approach. Okay. They try to discriminate it. They don't want to look for the overlapping. Okay. Whatever techniques they use, whatever discriminatory functions they use, they try to separate the class. That's all. Okay. So just see this one, as I was already giving you this example. Age and income, based on these two features, we have a two class label. One was defaulters, another one was non-defaulters. So this one is a better projection, this line W, because they are capturing, you can say, the data. If I project like this, there will be a clear separation. So this line is a better projection. If I draw a line like this, there will be more overlapping. So this is not a good, you can say, the projection, this one. This is a good projection, LDA, this W1. So we will look for this W on only this LDA. If it is LDA1, this axis, then we will only retain this LDA1. Okay. So this is a clear separation of this, you can say, the defaulters and non-defaulters class. Okay. I think if you are able to understand the logic, that is good, because in LDA we are also reducing the dimensions, because if it was a, let's say, 5-10 let's say features, so obviously the problem belongs to those, you can say, the 10 dimensions features. Now we are trying to reduce those 10 dimensions to, you can say, the lower dimensions. Okay. And capturing the variance. So this is the, you can say, the beauty of this LDA. And also they classify. So there is added advantage. So it works as a classification algorithm also, apart from your all algorithms. For example, the one that random forest, maybe the naive Bayes, KNN, support vector machine. Sometimes also you use neural network. There are many classification algorithms, even the logistic regression, right? And the LDA has this inherent property of reducing the dimensions and classifying. Okay. So also it is, you know, saving your time, because if you have this problem of to reduce the dimensions, then you will look for this principal component analysis. And there are many techniques for reducing the dimensions. So you will go for those techniques. If you have a 15 features in a real life case, then out of those 15 features, using PCA or another, you can say, the techniques, you will reduce it. If you are able to reduce it to 10, then you will apply any, let's say, logistic regression, neural network, naive Bayes, KNN, support vector, any things, maybe the decision tree, then you will apply. But if you will apply this LDA, they will do this job of this dimension reduction in the, you know, in the same formula, or you can say in the same machine learning algorithm. Okay, it will do the two work at the same time, reducing the dimensions and classifying the class labels. So if you have a three, you can say three category, let's say defaulters, non-defaulters, maybe let's say high risk, low risk, and medium risk. There are three category of customers based on some features. So how you are going to classify it using this linear discriminant analysis? Okay, so the logic will be same. You will look for those axes where you are trying to capture the maximum separation between these two classes. This is a typical approach of this LDA, because as the number of class, you can say, are increasing, so obviously there will be a problem to understand it, right? Just see, if I draw a line like this, if I capture the variance, like this, there will be some overlapping. So typically LDA will try to rotate this axis and look for in every single iteration, they will look for the LDA axis, LDA1, LDA2, LDA3, LDA4, something like this. If it is a 3 class, they will give you 2 LDA, 2 axis. If it is a 2 class problem, then it will give you 1 axis, LDA1. Okay, just remember this. If it is a 3 class, you will look LDA obviously will give you 2 axis. If it is a 2 class, it will give you 1 LDA1 only. So using this formula, as I already said, the distance approach, the maximum separation approach, and the variance, they look for the axis which is fit for separating the class labels. Okay, so just see this real life application. Okay, and then we will look for application using this R. Okay, so I kept this session short, so I'll try to show you using R and Python as well. Okay, so in this application, just see, for example, unknown, let's say unknown disease is spreading within the city. Let's say, for example, during COVID, even we were unaware of this disease. So this was new to us, and also we were not sure that if someone has a high fever, if someone has a throat problem, if someone is sneezing, whether he has or she has this COVID or not. Uh, 1 minute, I'm audible. Am I audible?
Yes,
Am I audible? I was disconnected or what? Can anybody confirm? Hello?
sir, you are connected.
I was connected, right? Okay. So in between also type in so that, you know. Okay. So now 1 minute. I thought I got disconnected, so okay. In which that I'll understand. Okay, I'm active. Full screen is visible. Yeah, full screen. So let's say in COVID case, obviously we were unknown to the, you know, the kind of, you can say, the parameters which can judge that whether you have COVID or not. So let's say you live in a city where there is an unknown disease which is spreading, right? We are not sure what kind of disease it is. Okay. So in that case, the symptoms, let's say you have captured is, for example, if someone is suffering from those disease, unknown disease. So what are the symptoms of those disease? Let's say they have a high, let's say they have captured, someone captured the high blood pressure, they had high blood pressure, the pulse rate was high, and also they had a high, let's say, temperature. Or for example, they only captured people who were infected with this kind of a disease, and their symptoms were captured in terms of blood pressure, pulse rate, and temperature. Just think like this. Okay. So we have three data points: high blood pressure, pulse rate, and temperature. Okay. So let's say more than 100 patients were sent to, let's say, emergency room in the last 2 weeks. Okay. So because this is a serious case, people are not able to understand what is the disease, or even if they are able to understand. Okay. So because this disease is spreading fast. So let's say XYG hospital had the data points of 100 patients of blood pressure, pulse rate, and temperature. Okay, of 2 weeks, let's say. So let's say the doctor, let's say XYZ doctor, has collected blood pressure, pulse rate, temperature from the patients and non-patients for further medical analysis. Obviously, whenever you look for any medical analysis, obviously you have some historical data, right? So let's say you are an intern to XYZ hospital, and now let's say if you have 100 data points of some, you can say of let's say 100 patients and their blood pressure, temperature, pulse rate. Now you have these data points, right? And now you're intern, let's say for example, you're working as an intern to XYZ hospital. So, and doctor has given you a job, right? They are just telling you that build a model, build any model based on a logic, because obviously the patients has that disease or not, right? So now you have these data points. So how you are going to create a model? Let's say now you are pretty much sure that you want to use this linear discriminant analysis, right? So as a intern, how you are going to apply this? This is a typical case, right? So the job of intern would be, if a new you can say patient comes, how you are going to classify that patient, that whether he is infected with those virus or maybe that disease or not. So that will be a serious problem for a new intern. Okay. So just see, uh, so now as an intern you have just decided to go for this LDA, right? Obviously in any machine learning model you typically have this the training part. You try to train that model, right? So obviously as an intern you will use, through the historical data, try to train, let's say, linear discriminant analysis, because ultimately, let's say based on this data set you have a two class, one is infected and another one is not infected. So obviously whatever data points, let's say if you have 100 data points, you will train the model first, and then you will look for some to predict, how you're going to predict if a newcomer comes in, if it is infected or not. This is your job as an intern, right? So obviously you will have some data points. So how? Just see. So this one is, let's say, 7 data points. Had it been, let's say, just assume it not 7, but assume it as 100 data points or 100 patients. You can say their you can say the attributes or whatever you can say. So out of those 100 patients, they are infected, let's say. And also here there is a no class level, but there is some class level also. Okay. So blood pressure was, let's say, of the one patient was 138, and the pulse rate is 76, and temperature was 38 point something. Okay. And these are the some patients who was infected, let's say. And there is also a patient who was not infected from the historical data. So I'll show you another example, but just imagine it here. So using how you are going to model it. And also there are 8 non-patients. So obviously 7 plus 8. So these are the data points. Okay. The one is infected, has these number of, you can say the blood pressure, pulse rate, temperature, something like this. This you can classify the entire 7% as a infected, and these 8% is a non-infected. Okay. So now you have these data points, infected and non-infected. This is non-infected, this is infected. Okay. So now you can model it using LDA. Okay. If a new patient comes in, okay, then how you are going to predict it? This is the case. Here we only have a three, you can say, features, input features. And the last one, it's not visible, is infected one. Okay, this is a target, you can say. Also, here we have three features, obviously the similar features. And the target one is non-infected. The point is, had it been, let's say, 15 features, if we are capturing 15 features, then it would be tedious for us, because the model which we are going to create, it will create a problem, because there will be a chance of overfitting. Any patient comes in, a new patient comes in, maybe that model is much biased, that they are just predicting that he's a, let's say, a infected person. So in that case, it will create problem for us. Okay, obviously as a in the medical industry, if you are doing like this, if our model is not, if our model is overfitting, in that case prediction would go in a one direction. It means there will be a much more biasness in that model. Okay, so you have to reduce this biasness. Okay, so that is why in that case we try to reduce the number of dimensions, so that it will not fall under under bias, or you can say underfitting or overfitting. It should not go with biasness. Model should not be biased. Okay, so this is a typical, you can say, the data sets. Now just see, I'm just using one more example, and I'll show you using the R programming how we are going to model the linear discriminant analysis, a basic one. Then you will understand it, that in a real life scenario, how you are going to model this linear discriminant analysis if you have supervised data set. For LDA, your data points, there should be input output combination, numerical values should be there, and it should be supervised data set. Okay, it should not be unsupervised. In LDA, there should be input output, or you can say the features and target combination. Also, you can see the linear regression, or for example logistic regression data set. Okay, there had features and target. So on that data set also you can apply linear discriminant analysis. But the logic behind this linear discriminant analysis is that you should have, I mean, many features. If you have many features and there is no multicollinearity, in that case you can apply this linear discriminant analysis. Okay, so just see, there is a one case of Netflix, let's say. So this this OTT platform Netflix, I think you all know this Netflix. So it's very popular, and they obviously they produce high quality content, right, for digital media across the world, right? So this company Netflix is they are trying to measure this subscription. So how they are going to measure it? The subscriptions are measured in terms of money spent on subscriptions, that I have just I'm just saying it as a MSS, and watching time. There are the two, you can say, the features. Based on these two features, whether you can say customers are subscribing this Netflix or not, right? So the result of Netflix subscriptions by data analyst is given in the table. So I'll show you how I mean, based on this MSS and WT watching time, how this Netflix is deciding whether a new customers, if he or she comes in to our platform, whether he or she gonna subscribe to our Netflix, some of the subscriptions or not. Maybe if it had many subscriptions, then how they are going to subscribe it. So whether they are potential customer of this Netflix or not. This is our typical case here, right? So just see the data set here. I have just a small data set here. So money spent on subscription, let's say, is let's say all are in dollars, 2.95. This is the first customer detail, and they are investing, let's say, 6.63 hours. Let's say I'm just these are the hypothetical data. and they have subscribed this Netflix. So this is our historical data, you can say. So we have these data points right away. Okay. So how you can say a customers, let's say, if you see this one, the last one, let's say as an intern, you can say as a consultant to this Netflix, if there is a one customer or you can say a new person whose money spent on this subscription is $2.81 and he and she the watching time is 5.46 hours. So how we are going to classify whether he or she gonna uh, I mean go into this subscribed class or not subscribed class. This is our case. So as a consultant to Netflix, how we are going to predict the class level even by reading the dimensions. Okay. Or you can say by creating a LDA axis, a new axis based on these two features. So this is our case. Okay. I think you all can relate with this case. So this is typically a classification problem. Also, you can say, sir, I can apply logistic regression. Yes, you can apply logistic regression. But here I am looking for the maximum separation between this subscribed and not subscribed class. Because the beauty of this LDA is that they create a maximum separation between these two classes, subscribed and not subscribed class. Okay. But logistic regression has not that much power to separate these two classes. Typically, you get more of this type 1 error. But in LDA, their you can say the inherent tendency is to discriminate the class, right? Subscribed and not subscribed. Okay. So how you are going to model it? So let me show you. Is R Studio is visible? Can anyone confirm if my R Studio is visible to you?
No, sir.
No? One. Just give me a second. Now,
Yes, sir, it's visible.
visible, na? Right, okay. So just see, I think data points you all have seen. And also I have shared you in a folder in Google Drive, I think. Yeah. So my data are saved in Excel sheet. Just see Netflix LDA data.csv. Okay. I'm just running it. Just see. If I will run it, okay. So my data, in the R, if you see read.csv is gonna read the CSV file from this location, okay? The entire location, this location. So now if I write a command Netflix LDA, this is user defined, don't get confused. This is user defined, you can write it anything. But this is read.csv. I think you all might be aware of this Python, similar to Python read.csv because it's in CSV extension, okay? So whatever data points is there, it will display. There are 7 data points, or you can say that there are 7 customers whose data was there. So this, just see, WT and MSS is a feature input, you can say, and subscription, this word is output, or you can say the target, or you can say the class, or sometimes people say it a label also, but this is a class. Label is 1 and 2. 1 is subscribed and 2 is not subscribed. Okay. Only we have this 7, you can say the customers. Okay. Now, ultimately, we are going to predict a new customer. But before that, there is a library, you can say the package called mass in R. You have to install this like this, library mass. Because inside this mass, you can say package, mass package, we have a function of this linear discriminant analysis. That is why I've just installed this mass package, right? So now I think there is a one missing or what. So model, 1 minute. There is some command which is missing. 1 minute. Let me just give me a minute. I'll show you how you can model it. So just 1 minute, just confirm it if my screen is visible. Is my screen visible? 1 minute, right?
Yes, sir.
Okay. So this command, I was just missing this command. I'm just explaining you what is this. Just see this. I have used this command called model, okay, because I'm modeling linear discriminant analysis. So this is also user defined. You can also write model 1, 2, 3 or something in any way, okay, even in capital letter, okay. And LDA is linear discriminant analysis. You have to write the way it is written. It's a function here. Subscription is a target variable. MSS and WT is features. We have only 2 features. Based on these 2 features, we are predicting subscription. This is a target variable from our historical data. And our data is saved in Netflix LDA, let's say. Okay. Yeah, data is saved in Netflix LDA. That is why data equal to Netflix LDA. So because we require this data to execute this command, subscription equal to, or this tilde sign, relationship sign. Okay. So what is this prior? This is a probability. Okay? If you see this one, how many class levels are 1? There are 4 out of 7. Okay. So class 1 subscribed is 4 out. Subscribed is 3 out of 7. We have to put this. Okay. Then only LDA will work. This is a probability, prior probability. You all know it because of this historical data. Out of 7, 4 are subscribed and 2 are not subscribed. Okay, 3 are not subscribed. Okay, and then we run it this a command called model again here. Then this will give you some probability. So this will give you the probability of subscription is 57%. And probability of this you can say not subscription is 42%. Okay, so MSS money you can say spend, and WT is watching time. These are giving the group means. Okay, as I already was saying, the group mean of the class. Okay, and this is giving you LDA one. This one you have to look for this LDA. This means this is a new axis. How they have created this new axis? So based on these 2 class label, they will give you the coefficient of this MSS and WT. So LDA 1, you can write LDA 1 equal to minus 5.18 5380 multiply by MSS, this one, plus WT multiply by this coefficient. So LDA 1 equal to MSS multiplied by this coefficient plus WT multiplied by this coefficient. This will give you a axis. So this is, you can say, a formula, a equation, a mathematical model for predicting a new class. If I know MSS of new customer and WT of new customer, then I can easily predict it. If I put in this one, in this formula, I can easily predict the class. So now I'm predicting how, let's say a new customer, this new data, a new customer, let's say a new customer, 1 minute. Yes. New dot data. This is also user defined. New data means you can put in anything. I have just written new dot data. I'm just making it a matrix form. And I'm saying the new data, I mean the new customers have money spent on this. You can say the subscription is $2.81. There is a new customer. Now I have to predict it. And whose MSS is 2.81 and whose watching time is, let's say, 5.46 hours. Or let's say I'm just reducing it to, is reducing or not? 1 minute. Let's say, let me reduce it. Let's say I'm reducing the watching time to 4 hours. Okay. So now it's done. I'm just creating a new, you can say, yeah, okay, this is done. New data is done. Rows and column. In column, you can say, I'm just saying MSS and WT. Corresponding to MSS and WT, this we will type in 2.81 and 4 hours. Okay. Don't get confused. Okay. And we are creating a data frame. You can say e.f.new is a data frame in R. So they will capture new.data in a row format, row and column. MSS and WT, and corresponding to MSS 2.81 and corresponding to WT, here it will come 4.0. But the crux is that we are predicting a new customer's, you can say, classification, whether he will subscribe to our subscription or not. If he has a money spent is $2.1, he is spending, if it is he or she is spending $2.81, and their watching hours is 4 hours, let's say. So where he will subscribe, he or she will subscribe or not to Netflix. Now, this one is a predict class. I'll explain you what is this. So this is now coming into class 2, means he will not subscribe, he or she. So this is a predict function in R. Model, which is coming from this modeling, because in model it is there, this one, entire this one. This entire is there in the model. Okay. And new data, obviously new data is this 2.81 and 4.0, and df.new, and this dollar class, this will give us the class level. Here this is giving us a 2, means not subscribed. Okay. So now we are able to classify it by creating a, you can say, a linear discriminant. It was a 2 class, subscribed and not subscribed. That is why we have got only one LDA projection, only one axis. Had it been a 3 class, we would have had LDA1, LDA2 as well, and their coefficient. So this is a model, you can say. This is our model. Based on these models, if a new customer comes, also you can multiply it here, and also you can see minus 5.81 multiplied by 2.81 plus minus 2.16 multiplied by 4.0. Just see what you result get. Okay, so we can also through this approach also you can predict in which class a new customer will come in. Okay, so this is how you can model using R. So let me share. Okay, hope this screen is visible. Okay. So now you can see the, this was our data set. So up to 6 data points I have used for training purpose, up to six data point, and 7th I have used for testing because it was unseen to our model. Okay. And now when I feed in this 2.81 and 5.46, let's say, now it is saying not subscribed. Okay. So this is how, as a consultant, also you can help your organizations that you go for this LDA because they achieve maximum separation and there is a less chance of committing this type 1 error. Okay. So mathematically, programmatically, we did it like this. Read.csp, then we applied this linear discriminant analysis, target variable, these are two features, data points, and we picked up this prior probability. And then this has given us other group means, and also they have given us the linear discriminant. These are the coefficients of this linear discriminant. This is the axis, the equation of this axis. When I draw like this axis will like this or like this. Okay, this will be x or y or like this. So this is the equation of this axis. So linear discriminant is nothing, it's the equation of an axis. And also they create a class separation. Okay, this is how you can understand as a LDA, linear discriminant analysis. Okay, so it was a new customer. Okay, so new customers had this information with us. The only features, obviously we will not have a target. Now we are looking for the target. When I apply this 2.81 and 5.46, we are saying no, means new customer is not gonna subscribe. Okay, so this is how we can predict. So now how, I mean, there are different assumptions of this linear discriminant analysis. Okay, so when we will come to know that, I mean, when you are applying this linear discriminant analysis, then also you assume something. For example, in case of logistic regression, also we assume something, and there are some assumptions. Okay, and also for, you can say, linear discriminant analysis, logistic regression, simple linear regression, we all have some kind of assumptions. So assumptions are like, for example, every features or either the variable, dimension or attributes in the data set has Gaussian distribution. Gaussian distribution is nothing but your variables, or you can say the input features, must be bell-shaped curve. It is written, right? A bell-shaped curve. Bell-shaped curve is nothing, something like this bell-shaped curve. Each feature holds the same variance and has a varying value around the mean with the same amount on the average. We are just targeting it to be a bell-shaped curve. Okay, each feature is assumed to be randomly sampled randomly. If your feature is sampled randomly, it means it will look like a bell-shaped curve. I mean, they are also, only the crux of this assumption is that your feature should be feature must follow this Gaussian distribution. Okay, the lack of multicollinearity, this is very much important. If your features have higher degree of multicollinearity, your model will be biased and it will overfit. So you have to reduce this multicollinearity, or you can say the curse of dimensionality. If you are able to reduce the dimensions, you can easily reduce this multicollinearity. For example, a square feet and maybe the number of rooms. If these two features are highly collinear, then you have to drop one. Okay. So when you want to, when you typically use this linear discriminant analysis, what should be the hint that you should use this linear discriminant analysis? Because you have many, you can say, even the dimension reduction approach as well as the classification algorithm. If you have to use these two, then why we should use this linear discriminant analysis? So you want to use one variable in prediction of another, or you want to quantify the numerical relationship between the two variables. For example, what is, let's say, the relationship between two variables, means what is the relationship between MSS and WT in case of Netflix. Other kind of algorithm is not gonna give you, but this linear discriminant analysis will give you that how one variable is related with another variable. The variable you want to predict, dependent variable, is categorical. If you have a dependent variable, if it is categorical, then you can apply linear discriminant analysis. And also you can apply logistic regression. There are many. Okay. But this is not a hint, I can say, for this linear discriminant analysis, but this is one of the hint you can say. And obviously your dependent variable should be continuous. Okay, so it is sounding like a logistic regression by the last two, the logic. Now also in logistic regression, your dependent variable are continuous, and also sometime it is in logistic regression, it is categorical one. But also it will work if dependent variable, or continuous. It should be, it should not be dependent variable. It should be, independent variable. Okay, here. So yeah, now how this linear discriminant analysis is same or different from this logistic regression. Okay, so linear discriminant analysis is as I already said, it's a classification algorithm and which uses Bayes theorem. Why it is using Bayes theorem? When you will learn this k nearest neighbor or maybe the naive Bayes, then you will understand the Bayes theorem, because they also use this probability, as I already said, out of let's say 7 you can say the subscriber, the 4 has subscribed it and 3 didn't subscribe it, so they were using this Bayes theorem. Okay, so linear discriminant also uses this Bayes theorem to calculate the probability of a particular observations to fall into which class, whether subscribed or not subscribed, right? It has an advantage over logistic regression. What is advantage? What kind of advantage has this linear discriminant over this logistic regression is that it can be used in multi-class classification problem. Just remember that if you have a data set where you have more than 2 class level, then you will obviously go for this linear discriminant analysis, because it is relatively stable when the classes are highly separable. Okay, so that is why it makes LDA is much better classification algorithm than other algorithms, right? And also here on the right side, if I compare with logistic regression is less reliant on basic assumptions of the data like normality and constant variance, more accurate on borderline points for some data sets. So if we have a binary classification problem, in that case, it's better to use this logistic regression, because if you have some class label which are in the borderline, whether you should categorize as a subscribed or not subscribed, in that case also this logistic regression can give you much better result. But obviously I'll tell you to go for this logistic regression, because ultimate aim of this this linear discriminant analysis is to create a maximum separation between the 2 class labels. Okay, so there are some before I go to the application part, let me show you the Python programming. 1 minute. So just give me 5-10 minutes, then we can easily Python programming. 1 minute. Python. Okay, so for Python programming, what is the window? Okay, so I think my screen is visible to all of you. So 1 minute. So for linear discriminant analysis, how you are going to model it in Python, right? So also I have shared you the data set of this linear discriminant analysis in Google Drive. So it's a similar, I mean, NumPy is a NumPy and pandas library, you will use it. So once you just run it, and my data set is here locally, I have shared you the online.csv. And if you run it, just see the features are, what are the features of this online.csv. This data set is, just let me explain you this data set. This data set is of some e-commerce company, right? So that e-commerce company is capturing some, these are the some features. Based on these features, whether a customer is providing revenue or not, whether they are purchasing from, from this e-commerce platform or not. So revenue 00 means they are not purchasing, they haven't purchased, but there are many customers who purchased it, but we are in the head, we are only, displaying only 5 records. Okay. So let's say exit rate, bounce rate, page value, those who are, know this digital marketing and all might be knowing this exit rate, page value. These are the features which are, they have captured from some e-commerce websites URL. Okay. And this last one, revenue, just remember it. This revenue is your target variable. Just remember this. And all other are your features, rest 14, 15, whatever. Okay. So when you run it, just run. So X is your feature and Y is a target. Okay. You now understand it. Revenue is a target. Just I splitted this into training and testing. Just see this one. Training data and testing data. So test size is, I am just using 20% for testing. Random state means for testing, when you are testing, you can pull out from, let's say from anywhere. Okay. So this is a random state, you can pull out from anywhere. But 20% means I'm just using 20% for test and 80% for training data. Okay. I'm just using feature scaling because there are many, you can say the features which are not in range, same range. That is why I'm just trying to scale it. That is why it's a feature scaling. For example, if age and salary, age might be in 2 digits, but salary might be in 7, 8 digits, right? So the both are not in the same range. That is why we try to scale it in the same scale, right? I think scaling is not working. I don't know. Xtrain. Xtrain is not defined. Why it is not defined? Straight. Okay, I haven't run it, so okay. Xtrain is not working. Now it is working. Okay, feature scaled. Now I have scaled it. This one, this you can say the library I'm using, or I'm using it for linear discriminant analysis. I'm just importing it, okay, from sklearn.discriminant analysis from here. Okay, so if I run this command, okay, and then LDA equal to linear discriminant. This is modeling. I'm just trying to model it. Okay, this is a linear discriminant analysis is a function, and I'm capturing this into LDA. LDA is a user defined. Okay, then I run. Then if you run it LDA.fit, you are just fitting Xtrain and Ytrain. Okay, the training data. Xtrain means you have a input features, whatever in 14, 15 features, and corresponding to this Xtrain, you have Ytrain means output or target or class. Okay, that is why this is a modeling. I'm fitting the model, LDA model. That is why fit function, LDA.fit command. Okay. So, and then you just run it, and new features. The variance, how much variance is being explained, because there are two only class level. One was, they are purchasing it, or, and another one was not purchasing. There is only one, you can say the two class. If you just run it, I think X test means you are just trying to predict and testing it how they are predicting the class. Okay, so it's a similar to logistic regression, just almost similar commands to logistic segregation. If you're trying to predict, making a prediction, okay, and this one is quite important. This one, confusion matrix. You just run it. This confusion matrix. Just see the type 1 error. You can say this one. So we are misclassifying it. Okay. We have predicted that 292 customers is not going to purchase it, but actually they have purchased it. It's not a problem. But here, just see. We have predicted that 45 customer will predict it, but actually they didn't predict. I mean, they didn't purchased it. So this is a problem, because if you have some, you can say some materials which you have already ordered it in advance. So in that case, it will create a problem, right? So 45 customers are not buying anything, and you actually predicted that they will buy it. Okay. So this is a problem here. But this is not a problem, 292. Okay? Depending on the inventory management and all. If you have inventory, then it is fine. If it is not, then there's a problem. So now I'll go for the accuracy. If you go for the accuracy, 86%, the accuracy is good, right? So for this e-commerce company, if you are able to achieve this accuracy, then it is good. So coming to this command, LDA equal to linear discriminant analysis, we are saying we are creating only one axis because there are two class levels. So we will create only one axis. Solver is, you can say, the mathematical approach to come up with some kind of a linear discriminant. This is you can say the discriminant function, right? And they will say the covariance is false. We are not capturing this covariance and all, and this is a tolerance level. So it could typically we keep this tolerance level of 0.001. So this is a traditional approach. But once you run it, what I'm just trying to explain you is that once you run it, just see this one. Go for this one. This one. LDA dot explained variance, how much variance that is being explained. This is the, you can say, the coefficients which I have shown you in R, the coefficients of those 14, 15 features. Only this is available. This is dot dot because 14 feature was there. So only few features they have shown it. These are the coefficient. So based on this, we can create a equation LDA 1 equal to feature 1 multiplied by this, feature 2 multiplied by this, feature 3 multiplied by this. Okay. So this is the equation which I was just trying to show you using both R and Python. If you have this, you can say the equation of this new axis, you can easily predict if you have a new or you can say the unseen customers, whether he will purchase or not. Based on these coefficients, you can easily predict it. Okay. So this is how in Python also you can model it if you have a different problem. Here the data set was huge. Just see the data set. So also and there are many features. So they have reduced it and they have also classified it. Okay. So this is how LDA works. So in Python you have seen it. So now just few applications and then we will close. It is visible, yeah. So okay, so if you see the applications of this linear discriminant analysis, so yeah, obviously you know that LDA is used for classification tasks, and also LDA can be used for some speech recognitions, maybe in the natural language processing, face recognitions. Even you can apply it for image retrieval. Also, obviously, in a bioinformatics, chemistry, where there is some kind of a class level. In that case, you can apply this, this linear discriminant analysis. So for one of the first, you can say the application of this LDA here, I just want to discuss is the customers recognitions, right? So LDA helps here to identify and choose the parameters to describe the components of a group of customers who are likely to buy some similar products. For example, in Amazon and all, so you might have seen someone has purchased this, so they have also purchased that, right? So they also use in the back of that applications, they use also, apart from this market basket analysis, maybe a naive base, maybe logistic regression, they also apply this kind of this LDA, right? So somehow they are going to classify who are their loyal customers and who are going to be the potential customers, right? So LDA can help you out by creating a clear distinctions between the two class, if it is a two class problem, if it is a binary problem, right? So this is how your LDA will work to classify, right? Also, you can use it for this, you can say the facial recognition systems. There are many, people who are working in this computer vision domain. They use this many algorithms. They use this linear discriminant analysis also, because there are many features. If you see the face has, you can say, more than 100 features. So based on those features, how you are going to predict whether it is you or someone else, by looking or by comparing it to your test data or maybe the training data, right? So facial recognition systems, when you are developing these facial recognition systems, in the field of this computer vision, it's also one of the part of AI, computer vision. Every face is drawn with a large number of pixels values. So every pixels will tell you, you can see the feature, right? So LDA reduces the number of features. Obviously, when you are working on any computer vision systems, you typically face this problem of higher dimensions. So as I already taught you here, this LDA, the work of LDA is reducing the dimensions and then classifying it. So in computer vision techniques, it's a best suited, you can say, the algorithms they typically employed for computer vision AI systems development, right? So they reduce the number of features to more controllable number first before implementing the classification task. So a temple is created with newly produced dimensions, which are linear combinations of the pixels value. As I already said, once they reduce the dimensions, so they will have some linear combinations of coefficients. As already you can recall it, in case of Netflix, we have two features, MSS and WTT. And corresponding to that, when I applied it in R, they have given us some coefficients. So here they are also saying the same thing. A temple is created with newly produced dimensions, which are linear combinations of the pixel values. Okay. So this is how these applications are one of the best in, you can say, the computer vision, right? So third one is in medical industry. Obviously, if someone has some kind of a disease, right? So, and if you want to classify the you can say the patient's disease in mild, moderate, or severe, if someone has a COVID, let's say, based on various parameters and the medical treatment the patient is going through in order to decrease the moment of treatment. So in that case, because it's a classical case of this classification problem, and also you want to reduce the some features, in that case, LDA can work better by separating the class level, because here there are three class level and one is mild, moderate, and severe, right? There are three class level. So if you have a more class level to predict, it's better to go for this linear discriminant analysis, because they will give you a better, you can say, predictions, right? So now coming to this one, I think anybody know who is she? Just type in if anyone knows. Anyone knows? Am I audible? Who is she? Okay. So this is a robot. Yeah. So this is a humanoid, a robot called Sophia. This was developed by Hanson Robotics. I think you might be knowing it. So I assume it. So Hanson Robotics, they have developed this robot humanoid, a robot looking like a human, right? So I mean the robotics is also a part of you can say the AI. So I have explained you a term called reinforcement learning, right? And also, I think you might be knowing of the natural language processing, computer vision, obviously the MLDL, you know it. So the Sophia, you can say this robot is built on natural language processing, computer vision, this MLDL approach, and also this reinforcement learning, right? Whenever they do any mistakes, they try to, correct it, right? The self-learning, they train themselves, right? So in learning nowadays, robots are trained to learn and talk to, and also obviously work as a human beings. Robot doesn't have feelings, but as you know, our AI models are maturing, a time will come, I think, they may not match the human capability, but at least they will try to catch up, right? The human intelligence, the human emotions. So this could be, you can say, you can also use it for the classification problem. Many, I think, the robots, and also in the learning approach. So maybe if you see these robots, if they use this linear discriminant approach, let's say if that, I mean, ML model is feeding into this model, so they gonna if someone asks any questions, so typically they try to group the questions based on various parameters, maybe sounds, tunes, speeches, right? And then they give you the answers, whether it will fall under a political category or it's a, let's say, entertainment. So there is a constant fight of this classification problem even in humans, right? So is with robots. So the what I was trying to tell you is that LDA is one of the finest algorithm when it comes to reducing the dimensions and classifying, right? So these all are the some applications of this linear discriminant analysis. Okay, so this is all from my side. If anyone has any questions, they can ask, or anyone has any questions? If not, then we can close the session here. Sweta is here. Hope I'm audible. If anyone has any question, you can ask. Otherwise, we can close the session.
Anyone has any question, you may put in the chat box.
Okay, I think no one has any questions, so it's better to close the session. Okay, and hope you have enjoyed it. And if you have any question, you can write into my email. Okay, so we can connect there. Okay, thank you so much
Thank you so much, sir.
for participation, and thank you.
Thank you, sir.